Hi, and welcome back to our flipped chemistry classroom. And we are discussing kinetics of reactions today. So we're moving into talking about equilibrium, but before we can talk about equilibrium, we need to talk about what makes a reaction happen, what makes it happen more quickly, what makes it happen more slowly. And so it sometimes is helpful to think of chemical reactions as kind of like the balls on this pool table, as molecules colliding in the same way that balls collide on a pool table, and it causes those balls to move in different directions. When our molecules or our atoms collide, it causes them to move in different directions, to have different energy, and occasionally to react with one another. And so we're going to talk about how quickly that reaction happens, the rate of reaction, how we measure that, and we're going to talk about what factors that depends on, as well as what a catalyst is and what role it plays in changing the rate of a reaction. So first thing we're going to talk about when we talk about kinetics is this idea called the collision model. So just like Tiger Woods strikes a golf ball, when we have the collision model, what we're talking about is that the collisions between the molecules, or the collisions between the atoms, have to have enough energy to produce the reaction. So we're going to talk about something called activation energy. And activation energy is the energy that's required to get a reaction started. So whether a reaction is endothermic, meaning it requires energy, or exothermic, meaning it gives off energy, there's always some activation energy that has to be met. And so the collisions have to have enough energy to exceed that activation energy. And then the other piece of the collision model is that the reactants have to have the right orientation. So they have to collide with the correct configuration. So you can't have one end of a molecule collide when you need the other end to collide. So we have to have two pieces. Our collision model says that there are two pieces to an effective collision. It has to have enough energy, and it has to have the right orientation or the right alignment. So when we talk about activation energy, we're talking about the minimum energy that's required to transform our reactants into what we call the activated complex. So the activated complex is the thing that we have kind of in the middle between the reactants and the products. There is frequently a complex, something that is the molecules all stuck together before it breaks apart into the new products. And so another way to talk about activation energy is this is the minimum energy that's required to produce an effective collision. So we have lots of different ways of providing activation energy. We can, as we have with these spark plugs, we can provide a spark. We can provide that activation energy through a flame, through high temperature, through radiation, even through light. So there are lots of different ways to provide energy to a reaction. Some reactions have low enough activation energy that they occur at room temperature. If we think about striking a match, that's a reaction, and simply the rubbing of the match against a rough surface gives it enough activation energy to get that reaction started. So we have lots of different sources of activation energy. So lots of different ways to get that, but they all have to have some input of energy, small input or a large input. So going back to thermochemistry, we remember that an exothermic reaction is a process where energy is released as that reaction goes forward and the surroundings get warmer. And you might remember these reaction coordinate diagrams that showed the energy in the system as a function of essentially time, the reaction going forward. So in our exothermic process, the energy of the reactants is high. They have a high potential energy. We have to put in the activation energy to get the reaction started, but once we overcome this activation energy barrier, once our collisions have enough energy, then it's all downhill from there, and lots of energy is given off, and the products have a much lower potential energy than the reactants. And we remember that this overall change is the delta H of the reaction, or the enthalpy change of the reaction. So reactants, activation energy, energy of products. And if we were to draw our activated complex, we would draw it right up here at the peak of this hill. So when we get to the activated complex, we have reached the activation energy. An endothermic process, our map looks much the same, just sort of the opposite direction. So this is a process where energy is absorbed as it proceeds and our surroundings become colder. So our reactants have low potential energy in an endothermic process, and our products have a high potential energy. But you notice that we still have this activation energy. So there's still more energy required to get this reaction started than even there is for it to finish. So you notice that the activation energy of an endothermic process is really large, and the activation energy of an exothermic process is relatively small, because the activation energy of an endothermic process includes the enthalpy change of the reaction plus that additional energy. Okay. So when we talk about reaction rates, we are talking about the rate at which a reactant disappears. So in this case, our nitrogen dioxide is disappearing, the concentration of it is decreasing. Or we can talk about it as a appearance of a product. So we can see that our nitrogen monoxide is appearing and our oxygen is appearing. So we can measure either the disappearance of the reactants or the appearance of the products. And of course, because these are molar concentrations, they're going to be stoichiometrically proportional. So because our nitrogen dioxide, 2 molecules of nitrogen dioxide decompose into 2 molecules of nitrogen monoxide and 1 molecule of oxygen gas, our nitrogen dioxide and our nitrogen monoxide is going to disappear at the same rate at which nitrogen monoxide appears. But nitrogen monoxide is going to appear twice as fast as oxygen does, because for every 1 mole of oxygen that's created, 2 moles of nitrogen monoxide are going to be created. So we measure reaction rates as change in concentration over time. Okay, so what things can make our reactions go faster or slower? So what factors affect rate? So things you might typically think of: temperature, because as we increase temperature, we are increasing the energy that each of our molecules has. Remember that temperature is directly proportional to kinetic energy. And so that means that more of the collisions are going to have higher energy, and that higher energy is more likely to exceed the activation energy. So that means more of our collisions are going to be effective collisions. Surface area, we can increase surface area. That's also going to increase the rate of a reaction, because increasing surface area is going to increase the number of collisions that are going to happen. If we have a small surface area, only the surface is available to react. But if we have a large surface area, then we have lots more potential locations for those collisions, and therefore more potential for effective collisions. Increasing concentration. So when we increase concentration, this is usually going to increase the rate of a reaction. And we'll talk about when we start determining reaction rates, why that is that it doesn't always. But generally speaking, increasing concentration is going to increase the rate of a reaction. And then, of course, the presence of a catalyst. So a catalyst always makes a reaction go faster. And the way that a catalyst does that is usually by providing an alternative pathway. So if we go back to these reaction coordinate diagrams, if we provide an alternative pathway that has a lower activation energy, that means more of our collisions are going to be effective. And so that's one of the ways that catalysts can make reactions go faster. So increasing temperature always increases the rate of a reaction. Increasing surface area also always increases the rate of reaction. Concentration usually increases the rate of a reaction, and a catalyst increases the rate of a reaction. So how does concentration of reactants increase the rate of reaction? Well, as you have more reactants, as the concentration gets higher, the likelihood that those reactant molecules will collide gets higher. So if we try to burn steel wool here, it will react, but it's relatively slow. It doesn't burn very fast. If, on the other hand, I take that same steel wool and I put it into pure oxygen, I've just increased the concentration of the oxygen, because our air is not a lot of oxygen. 18% of our air is oxygen. But here in the pure oxygen, I have greatly increased the concentration of my reactant, and so I get this very fast reaction. So when we have in air, it's slow because our concentration is low. In pure oxygen, it's really fast because much higher concentration. So how does a catalyst increase reaction rate? Because it lowers activation energy. And we have a couple of different ways that that can happen. When we go back to biology and we talk about enzymes, these are usually proteins that catalyze biological reactions. And they usually do that by holding the molecules in a particular orientation. So they actually affect the orientation piece of the collision model. So they make it so that more of the reactions occur with the right orientation. It can also provide an alternative transitional complex that has a lower activation energy. Homogeneous catalysts are present in the same phase as the reacting molecules. So this is very often the case in biology, where you have the enzyme in solution with everything else. A heterogeneous catalyst is present in a different phase than the reacting molecules. So when we think about like a catalytic converter in your car, that catalyst is a solid, but it's catalyzing a reaction that's happening in the gas phase. So that's a heterogeneous catalyst. So let's take a look at a couple of reaction coordinate diagrams. So this is an endothermic reaction, we know, because we have low energy of our reactants and high energy of our products. And without the catalyst, we have a really high activation energy. But with the catalyst, we have a much lower activation energy. And because we have a much lower activation energy, this means that more of our collisions are what we call effective collisions. More of the collisions will have this amount of energy than this amount of energy. And so that means that more reactions will be effective and our reaction will go faster. When we look at an exothermic reaction, even though the exothermic reaction has a lower activation energy than the endothermic, it can still go faster when we add catalyst, because again, it lowers the activation energy even more. And so by lowering that activation energy, again, more of our collisions are going to have enough energy to get over this hill, then over this hill. And so our reactions will happen faster. And remember, we measure reaction rate as change in concentration of a reactant or a product per unit of time. So change in concentration over time. All right, that's it for kinetics. As always, I look forward to hearing your questions and seeing you in class.